All right, good afternoon. Let's start the lecture. Okay, the midterm finished, marking, and T has helped recording, upload the grades to the Connect. So you should be able to see your grade now. And you can see your grades for each question and then also the total mark. Okay, yeah. 3 of us, 2 TAs and me, and so we marked the question each. So it should be fair. I mean, use 2 questions each, but there might be a different sort of a style. But I do give them a criteria in terms of marking, right? If you, I will return the paper back to you guys next Tuesday, okay? And if you can't wait, just come to my office and I'll find yours too. If you notice any discrepancies, if you have any concerns, feel free to come to me, okay? And show it to me, and then we can look it together, right? Yeah. Is that good? Yeah. I haven't really got a chance to calculate average there, but the TA said it's around 70%. I wonder whether it's above 70 or below 70. But anyway, so it's not too bad, but it's not. Should have been a little higher, I think. Yeah. Okay. There at least there's 1 or 2 students got 100%. Yeah. Okay, so let's continue on the lecture here. Okay, so we have a little bit on the gear train and gear force concept, and then we'll get on to basically the helical gear, but then I'll get on to the basic design concept for spur gear. So in the previous lecture we talked about gear trains. So now let's take a look at basically the gear force for spur gear first. So when you have a spur gear, chances are, you have a pinion trying to drive a gear. Okay, so one smaller one trying to drive a relatively bigger one. Okay, the direction of rotation is probably this way here, and then this one will rotate at this direction, right? Okay, so the 2 circles that are here basically representing the 2 pitch circles, and depends on the choice of the gear. So you would have basically the so-called action-reaction line or line of action, and that purely depends on the pressure angle, right? So here's your pressure angle right here. So the force from one teeth to the other, okay, is along the direction of this line of action given by the pressure angle, okay. So now question basically is the free body. We want to look at the free body diagram for the system right here, okay. So you have a force, essentially if you have a pushing force from the pinion side, then you have a basically reaction force from the gear side, right? Yeah. So we should essentially, it doesn't matter which one you look, whether you look at is the gear or the pinion. So that really doesn't matter there. So let's just take a look at one of them. That should be enough. Okay. So I'll just draw a circle like this. Okay. Yeah. So let's just say this is the one here. Okay. So this is we're looking at the free body diagram. Okay. For the gear at here. Okay. So what's the free body diagram? So if you look at the force at here, so you have a force. So remember, the gear is carried by a shaft. Okay. So there is a shaft going through this gear, right? Going through the gear here, and the gear is being pushed basically by the pinion, which is in this direction, right, from the top to the bottom here. Okay. Then basically we can have a force, okay, which pointing to this direction at here. Okay. So let's call this is W at here. Okay, let's call this W. So that's the amount of force applied from the pinion side to the gear, right? Okay, and that's the W. And then the gear itself will be driven by the shaft, and then there's a torque. So let's call this as TB at here. Okay, let's call this a T. And then because this is shafted here, right? This is a shafted here. So if you have a pushing force W here, then the shaft will result in the action-reaction force parallel to the W. Right? So applied from the action-reaction force from the shaft. So let's call this as FB at here. Let's call it FB. So that's basically the free body diagram, right? In terms of the gear at the bottom here. So you have a force at here, there's a torque, there's also action-reaction force from the shaft, FB, trying to balance this W at here. Okay? Yeah. Now, let's further break this force W into two components. Okay, so breaking down into two components at here. The one that goes through this center we call the radial load, WR, and the one that is horizontal we call that WT. Okay, so this is breaking down the W into the two forces. So WR is called radial load. And WT, and we call that transmitted load. Okay, the transmitted load. Then you'll see why this is called transmitted load, basically. Okay, yeah. And W is along the line of action here, and then which has a pressure angle phi with the horizontal. So this is basically phi angle here, right? It's phi angle. So you can easily see the calculation. Then WT equal to W times cosine phi, okay, and the WR equal to W times sine phi. Okay, so WT equal to this, and WR is equal to that. Okay. Yeah. So why the WT called the transmitted load is because, see, the WT is a horizontal force, and the torque basically is generated by WT because WR goes through the radial, the center at here. So WR does not generate any torque, and WT will generate the torque, right? And the torque generated by WT is what? WT times half of the diameter. Okay, so that's the amount of torque generated by WT. Okay, yeah. So if this is a D at here, then the amount of torque generated by WT is, yes. Which one? This TB? The TB is the reaction torque, basically, trying to balance this. Yeah. Okay. Yeah. So you often use a shaft to carry a gear, and another shaft carries the pinion. So the input power to the input shaft is going to be transmitted to the output shaft, right? Yeah. So basically the torque at here times your angular velocity will basically becomes the amount of power transmitted, okay, through this system at here. So that's why the WT at here is called transmitted load. Okay, so that load is transmitted from one end to the other end. Okay, yeah. Now in terms of the free body diagram for the pinion, it's pretty much the same symbol, but it's just change these directions, right? Change the directions. Okay, yeah, action reactions. So this is basically the force when you have a spur gear, a pair of spur gear acting together. That's the free body diagram. That's the force distribution. At the end of the day, you know, we're analyzing stress analysis or design for the gear, but also we're going to actually translate all the information to the shaft we're designing, where we're using it here, right? So if you imagine if you have a shaft at here, okay, if you imagine you have a shaft here, and this WT and WR will ultimately translate to the shaft location, okay, to the shaft. So if I have a shaft, for example, if I have a shaft here, and this is the location of the gear, and then you have basically WR and WT, right? Okay, then this is a WT. Then, but if you're talking about the free body diagram for the shaft, then what do? You basically get WT at here, and you basically get a WR at here, right? Yeah, and that is a typical situation. We call that two-plane bending. Okay, two-plane bending, which we have exercised quite a bit. Okay, so this is basically the spur gear. Okay, spur gear has two forces ultimately. One is radial load, the other is the transmit load. Yes.
What's the
H is the power calculation. Yeah. So actually, I'll talk a little bit just to refresh your mind on this power concept here. Okay. Yeah. So T times omega, which is angular velocity, huh? Okay, so that's spur gear, huh? That's spur gear, and now let's look at a helical gear. Okay, very quickly go through this helical gear concept. Okay, so in the, I think this picture is in the handout from previous lecture, but otherwise that's okay. So there seems to be quite complicated, but it's actually not. Okay, remember the helical gear. The difference is the gear is not straight. The teeth is not straight. The teeth is in the basically format of part of the helix, right? So if you extend the teeth, okay, curve the teeth to keep going, then you'll see this is basically part of the helix curve, okay, parametric equation helix curve. Okay. So that's the nature of helical gear. Yeah. In this picture here, it's illustrating. It is illustrated using the so-called helical rack. So essentially, if helix is generated using a circle. If you expand a circle to a radius of infinitely big, then you get this so-called helical rack, essentially. Okay, helical rack. Now, for helical gear, comparing to spur gear, the only difference, okay, is it has two sets of parameters. So if you look at within this AA plane, which is basically the front view, okay, the front view of this helical gear, okay. If you look at the front view, you basically you get exactly the same kind of view of a spur gear, right? If you look at the front view, okay, yeah. Now, if you cut this helical gear with this BB plane, which is basically the normal plane, normal to this helix, okay, to the helical curve. If you cut it, and you look into this front view of the BB plane, and you get not exactly kind of spur gear perspective. Okay, can you visualize that, right? If you're looking into the AA plane and BB plane, you cut it. From the viewpoint of view, nothing different. It's just all you see is still like basically a spur gear type of structure, right? But the parameters are slightly different. Okay, the parameters are slightly different. We have essentially two set of parameters. So the front view, the AA view, AA plane here. Okay, so this AA at here is called transverse. Okay, it's called the transverse direction. So that's the front view. And then the BB side here, this is called the normal plane here. Okay, the normal plane. So within each plane, from the user side, it's just same as a spur gear, but the parameters are different, and you have basically two set of parameters called the diametral pitch. So the Pn and the Pt. T is for transverse, N is for normal, and both are the so-called diametral pitch. Okay, yeah, both are so-called diametral pitch. Right. So in each plane, there is a value for the diametral pitch, and diametral pitch is a very fundamental value, right, for the gear. It typically takes 2, 4, 6, 8. Okay, then it goes up to 12 and then 20, 22. So there's a coarse diametral pitch and there's a fine diametral pitch. Okay, and in each plane, say this is the plane BB, this is plane AA. And you also have a small pt and small pn, which, if you recall that, we call that circular pitch, right? This is circular pitch. And circular pitch, this is along the pitch circle, right? Okay. So if it's a spur gear, if it's just spur gear, you don't have one set of numbers, right? But now for a helical gear, you got a two set of numbers at here. Okay. So if you look at this BB plane, so from one side of the teeth along the pitch circle to the same point and adjacent teeth, then you get the pitch, circular pitch. Same thing in the AA plane. Okay. There's a connection between the parameters at here. So these parameters here, there's a connection. So the Pn is equal to Pt times cosine phi. Okay, the phi at here is a so-called helix angle. The helix angle. So helix angle is the angle parameter referring to the helical curve for the teeth. Okay, for the teeth. If you draw a helix, right? If you draw a helix like that, okay, and if you take any point, okay, you draw a tangent line along that point, and here is the axis of rotation. If you look at the angle between the tangent line and this vertical axis here, so that angle is basically the so-called helix angle. Okay, that's the helix angle. For helical gear, you can actually specify what helix angle you want. The larger the angle is, then you actually, the smoother rotation it's going to be. Okay, yeah, the manufacturer usually will dictate the amount of the helix angle. Okay, it's not arbitrarily given though. And same thing, you can have a relationship between this diametral pitch between the two planes at here, and that relationship is Pn equal to capital Pt over cosine phi. Okay. So this is the connection for these two set of parameters at here. Good? Yeah. And also within each plane there are two sets of pressure angles. One is phi t, one is phi n. So there are two sets of pressure angles, right, in the transverse plane and in the normal plane. There are three angles. So if you take the cosine of the helix angle, you'll get this relationship. Okay, you get this relationship. So the two pressure angles are related to the helix angle. Okay, so they are geometrically, they can all be derived, okay, the relationships like this. Okay, yeah. And one last thing that's not actually exist for spur gear is the so-called axial pitch. Okay, it's called so-called axial pitch. So axial pitch basically is the distance if you're going along the parallel direction of the axis of rotation. If you're going along the direction of this axis of rotation, starting from one location on the gear and up to the next location, going along that direction to the next location in the gear teeth. And this distance here, from here to here, the A to D, okay, that's basically this is so-called axial pitch. Okay, axial pitch. So this axial pitch right here is px. Okay, it's the px right here, and the px is related to the transverse circular pitch. Okay, and then divided by tangential helix angle right here. Okay. So that's basically the parameters that are related to the helical gear. Okay, the helical gear. There is an example in my lecture notes. I want you to calculate the given certain number and to calculate all the other ones using basically the equations given at here. Okay. Yeah. So let me ask a very simple question here. So you see the axial pitch here, right? The axial pitch. This is the axial pitch. This is for helical gear. What's the axial pitch for spur gear, according to the definition? If you have a spur gear, what will be the axial pitch? See, the axial pitch for helical gear is starting from one location on the gear tooth, then you go along the axial rotational axis, and then the next location, adjacent location there, the distance is the axial pitch, right? Yeah. So what if you have a spur gear? The axial pitch will equal to what? Not zero. Spur gear, you have the teeth is what? See, this is a helical gear, right? If it's helical gear, the teeth actually what direction? The same direction as for spur gear, this is the direction of the teeth, right? So the axial pitch for spur gear will actually equal to infinity, right? Okay. Yeah. So anyway, take a look at the example in the lecture notes. Okay. I'll skip that example here on helical gear parameters. Okay. But what I want you to make sure to understand is the next one is because this could be you could be designing a gear using spur gear, and in that case you need to apply the following knowledge, basically the force analysis for helical gear. Okay, yeah, for helical gear. So this is just drawn only one helical gear is drawn. You can visualize that another helical gear and the pinion on the top over there driving this bottom of helical gear. Okay. So the W right here is the force in the normal plane. Okay, so W is acting normal to the surface of the helical gear tooth. Okay, so the W here is actually in the normal plane, and then this is the front plane. This is actually the transverse plane, right? The transverse plane. So now you can see, if you look at the W here, you can break the W down to three different components. One is the WA, WR, and WT. So WR and WT is basically the same notation as the spur gear. So WR is the radial load, and WT is the transmitted load, and WA right here, this is basically along the the shaft direction. The shaft direction. So A at here is called axial load. Okay, so this is different now, right? Spur gear doesn't have this axial load. But the helical gear, if you use the helical gear, then there will be a axial load generated, WA, and this axial load will ultimately can be felt by the shaft. Okay, so the shaft will feel this axial load, and this axial load ultimately, and you want it to transmit from the gear to the shaft, and then from the shaft down to a bearing, and the bearing down to the ground, basically. Okay, yeah. So in that case, as we learned the bearing, basically, if you have an axial load, and sometimes we also call it thrust load. Okay, so that load has to be taken by the bearing. Then the bearing has to be able to take some certain number of thrust loads. So you need a thrust type of bearing to take the load, essentially. Okay, yeah, that's the difference between the helical gear, fundamental difference in terms of force analysis. Okay, and spur gear. And in terms of mathematics, is quite simple here. So you can calculate your WR as W times sine pressure angle phi n. Okay, so this is the pressure angle, right? WR equal to top W times sine phi n, and then WT equal to W times cosine phi n and cosine helix angle phi. And finally, WA is equal to W times cosine phi n and sine helix angle. So this is the connection among all the three different components. Okay, yeah. In actual situation, when we do calculation, okay, often the procedure is what you're given is the amount of power. So you're given how much power that is required to transmit from one end to the other, basically. Okay, yeah. Then from the given power, you can calculate your transmitted load WT, okay, and also based on the design of your gear, of course. From the W, you can calculate WT. You can calculate your W. Then from the W, you can calculate either WR or WA. Okay, depends on the type of gear. So that's typically in the calculation, in the typical calculus analysis or design, the direction of going there. Okay. Yeah. Okay. So that's all about the force analysis for either the spur gear or the helical gear. Okay. Any questions? Good. Okay. So. Now we're moving on to the new topic. Basically, now we'll look at the design for a gear now. Okay, design for gears. But before we start the design for gears, I really wanted to touch upon a topic on torque, power, okay, and rotational speed, just to brush your memory in terms of calculation, the concept here. Okay. Yeah. In simple, when you talk of power, okay, in simple language, basically the power equal to the amount of work done over the time it is taken. That's power, right? Yeah. How much work is done within a certain amount of time. The tricky part in our course is we always deal with two different type of units. Okay. So we have a SI unit. We also have this American unit. Okay. So I'm gonna write down a few very commonly used formula in both of the units here. Okay, standards here. For SI units, when you calculate the power, okay, you can use the T times your angular velocity W, and the dimension at here. So the P at here is in watt, okay, or W, and the T at here is a torque, the standard unit is Newton meter, and omega here is the angular velocity. The standard unit is reading per second. Okay. So if you use all the standard unit, then you end up with your power, which is watt, right? W. Okay, so that's P equal to that. Now, often in time, what you're given, it's not reading per second. And often in time, what you're giving is revolute per minute. So that's very, very common, right? So your shaft speed probably is given in revolute per minute. Okay? If it's given in revolute per minute, and then the formula here will have to be slightly changed to reflect this change of the dimension here. Okay? So let's move down this a little bit. So how do we change that? So let's see, we still use a T times W, but right now this is N here, right? This is N here. So we need to convert this revolute per minute to readings per second. It's very easy. So 1 revolute is 2 pi readings, and 1 minute is 60 seconds. So you can just use a T times pi, 2 pi over 60, and that'll give you this conversion in here. The usage of this formula, okay, could be very well is given the amount of power to calculate the required amount of torque input. So you can inverse calculate the torque, and that gives you, okay, T equal to 9.55 capital P over N. So if this capital P is actually given in kilowatt, okay, so sometimes very high power, you describe that as in kilowatt, then the capital T calculation at here, okay, is going to be this much. So the capital P here is in kilowatts. Okay? So that's a standard unit. Okay, that's in standard unit, and that's the formula you should remember. So let's take a look at the US unit at here. Okay. Yeah, the inch series. In US, the power often is given in horsepower. Okay, in horsepower. So just a little bit background story at here, how horsepower is being derived. Okay, yeah. This is actually proposed by Watt, right? So basically what it states is, okay, it looks at a horse, okay, and turning a mill, okay, and then observe, it says, okay, so it's turning a mill 144 times in an hour. Okay, yeah. So that's how fast it's going. At 144 times in an hour, it's approximately 2.4 times per minute. Okay, 2.4 times per minute. And then in the standard mill, okay, it has a wheel. The wheel has 12 feet, okay, in radius. Okay, and it's assuming the horse, okay, travels. So now you have a standard size for the wheel, and you have the speed. So now you can calculate how much distance the horse travel, right? So basically 2.4 the velocity times the circumference of the wheel. So that gives us a unit of feet per minute. Okay, so the horse travels this much feet per minute, and the poor horse will be able to pull 180 pound force. Okay, 180 pound force. So with these numbers, then we can calculate how much of a horsepower now. Okay. So you get 1 horsepower is equal to the amount of force times distance, then over the time. Okay, amount of force times distance over time. So that gives you 180 pound force. Okay, and then 2.4 times 2 pi times 12. Okay, this is 1 minute out of here. So this calculation gives us 32572. Okay, and the unit is a feet pound force per minute. Okay, pound force per minute. So that's where the 1 horsepower is from. Okay, so it's from this calculation. And this number are typically approximated with 33,000 value. Okay, same units. Okay, yeah. So that's 1 horsepower. 1 horsepower equal to this much value here. Okay, this much value. So inside this calculation area here, as actually you can see now, basically you see there is this formula here, force times distance, right, and over time. And distance over time is velocity, so that's basically force times velocity. Okay, force times velocity. In this formula here, the F here, the unit is always pound force. The velocity here is always feet per minute. Okay, so always feet per minute. Yeah. So then the power here, okay, is basically this F times V. So that's your force times velocity, just like the T times omega. Okay. Then when you calculate your power using F times V, and you can convert that into horsepower. So ultimately you can use this divided by 33,000, you get the amount of horsepower there. Okay? Yeah, that's the connection. Okay? Yeah. Good. Yeah. Now, if what you're giving it here, okay, so what you're giving here is instead of basically actual velocity, often in time when you have a shaft design or gear design, and you inevitably will use this angular velocity, right? Use angular velocity here. So if what you're given here is n here is revolute per minute, okay? So sometimes what you're given is revolute per minute. So you can also derive, I skip myself some steps out here. You can also derive your power. Okay, in that case, your power will be derived to be this much now. Okay, yeah. Will be T times N over this much. Okay, so that'll be T times N horsepower. Okay, yeah, and T at here is equal to F times the distance, which is pound force inch. Okay, pound force inch. So that's the unit for the T. The N at here is revolute per minute, and the amount of the horsepower will be T times N, and divided by this number, you get the amount of horsepower. And this is sometimes approximately just 63000 horsepower. So that's the number of formulas. You should remember this one here. Okay, just particular for your calculation, right? Okay. So let's take a look at an example. Actually, by the way, I don't know if you remember how much is 1 horsepower equal to in terms of watt. 746. Yeah. Good. So let's take a look at quick look at an example here. Okay. So let's say we have a gear. with a number of teeth 16, diameter pitch 8. The gear is spinning at 1200 revolutes per minute, and the transmitted load for the gear is 365 pound force. So we want to calculate how much power is transmitted. Okay, how much power is transmitted for this simple example. Okay, so a simple calculation in here. So the gear has a number of teeth given, diameter pitch given, so we could calculate basically the pitch diameter. And you have essentially you have a gear at here. It's probably driven by a small gear pinion, and you have a linear velocity over here, and then the pitch diameter is over here. Transmitter load. Okay, transmit load is, you can also illustrate the transmit load is over here, right? Okay. So pitch diameter D, okay, is related to the number of teeth and the diameter pitch, like this. So number of teeth divided by the diameter pitch, and you get your pitch diameter. So 16 divided by 8, you get 2 inch. Okay. Yeah. And now we can calculate the pitch line velocity, V. So this is the pitch line velocity. This velocity here needs to be a constant, right? It needs to be constant here. So V at here is omega times half of the pitch diameter, omega r, right? Okay. And omega is given in terms of the revolute per minute, so that has to be converted a little bit at here. So this one here will be 2 pi n over 12, okay, and then times d over 2, okay. D over 2. So your V at here, basically you calculate, you get 268 feet per minute. Okay, feet per minute. So that's your pitch line velocity. So finally, you can calculate how much power is being transmitted now. So your horsepower is Wt times V, right? So your Wt times V, and then divided by 33,000 to convert that into horsepower. So Wt is 365, 628, and end up with approximately 6.95 horsepower. Is that good? By the way, the reason we're dividing 12 at here because this is an inch, so divided by 12, and finally convert that into the feet, okay, feet per minute. Because when you calculate this, when you use this formula here, that V has to be feet per minute, okay, feet per minute. So that's a simple example, just basically this formula here, and I encourage you to memorize all of these things here, okay? Yeah. Okay, so now let's take a look at gear design issue now, okay? Yeah. So for the first one here, we're going to look at the spur gear design. Okay, so we're going to look at the spur gear design first. Yes.
When you use H, you're mostly referring to horsepower, right?
Yes. When I use this formula here, we get the horsepower. Yeah. Because in inch series, when they describe the power, they use horsepower to describe, right? Yeah. Yes. We're keeping the minutes here. Yeah, so for inch series, the funny thing is the V has to be in the feet per minute, right? You see how horsepower is calculated, the story right here, right? It's in the feet per minute, so it's not feet per second. So yeah.
Yes. Have the imperial system for
you're gonna have both actually. Yeah. It's just like the textbook. Sometimes it's imperial, sometimes it's a standard unit. Yeah. Yeah, I know. Yeah, Canada use. Yeah, why does the gas station using gallon, right? No, sorry, this is what I'm talking about. No, gas station using liter, right? Was there anywhere? Oh yeah, when you buy grocery shopping using pound. So, isn't it right? So, but Canada use a metric system. I know, yeah. But if you go to the States, you talk about a centimeter. They'll ask, what's a centimeter? Right? So, anyway. So, unfortunately, you're going to have two different measurement system to get used to, though. Right? Okay, so spur gear, just to give you a bigger picture here, what we're going to do in terms of spur gear design. Okay? And then we'll slowly derive the equations, transition into the type of equation we use for spur gear design. Okay. Yeah. So first of all, I'll show you two pictures here. Okay. So two pictures to show you basically the type of a failure a gear that could experience. For analysis, okay. So this first picture here shows you the type of analysis, the method that you can use, technique you can use in terms of analyzing the stress distribution when two gear teeth are engaged with each other. Okay, so this is a so-called photoelastic stress analysis. Okay, yeah. So there's a reflective coating applied to the surface of the object, and then there will be some sort of a tool such as the digital polar scope. It will split this coherent monochromatic light into two beams and shines them on an object, and you'll see the cluster of basically a cluster of interference or fringes pattern at here, right? Yeah, and the density is actually different. So the density, the pattern of the density will indicate where the maximum stress will occur when two teeth are engaged with each other, pushing each other. Okay, so that's one way of doing the analysis here. Okay. So as you can clearly see in this picture, the maximum stress happens at this contact location, right? That's one location. And the other location happens where? At the root location, right? Yeah. So that's the two locations basically of interest to us. The first location happens at the contact location, when one gear is in contact, when one tooth is in contact with the other tooth, okay, and that's the location of interest. And this is the location, the root. This is actually kind of easy to understand because, as we're going to do, we can formulate a gear tooth as some sort of a beam, right? So when you have a force applied at one end of the beam, then the maximum stress will happen at the root location of the beam, right? So that's kind of easy to understand. And this one here is basically at the surface location, at this location here. So that's generally the type of surface we're going to differentiate us to different type of failure. One is called surface failure, okay, and the other type of failure is basically called failure. It's called bending failure, okay, at root location. Okay. So that's the two type of failure we're going to analyze, or we'll try to prevent from happening, okay, in terms of design for gear. And these two picture sort of shows you the two different type of failures. So this is basically surface failure. So surface failure happens when you have a pressure applied to the surface, okay, or when you have two objects in contact with each other, applying pressure to either side of the surface. Okay. And bending failure, essentially, of course, is something break down, and can due to the bending moment, right, or due to the bending normal stress. Okay, so that's the type of structure failure that you see here. Okay, yeah. So we want to prevent these two type of failure from happening. Okay, yeah, and we're going to use certain equations, okay, to derive or to prevent the to analyze or to design for the gear at here, okay, under certain loading. So but instead of directly jumping into that equation, okay, so there's a little bit of story at here as to how that equation is derived. Okay, so this basically equation is called ultimately there's a so-called Lewis equation. Okay, Lewis equation. Yeah. So we're going to look at a little bit of story here in terms of Lewis equation for two bending stress. Okay. Bending stress in here. Okay, so here's a little bit derivation. Okay, so just bear with me. I need to tell this story somehow. I feel this more completing the study here. So I get a couple of pictures wanted to show you here. Okay, yeah. In mechanics material, there's one thing that you probably didn't learn in mechanics material. There's basically you learn, essentially. Analyzing the stress distribution along the cantilever beam. That part you learned, okay? Yeah. This is, for example, a fairly non-regular cantilever beam. It's not a straight cantilever, but it's still you can consider it a cantilever beam in here, okay? But there's one situation. It's called, okay, uniform strength cantilever beam. Uniform strength cantilever beam. So what does that mean basically? So let's take a look at this. Take a look at this picture, the drawing at here. Right. Here's a beam, and you have a force applied at one end of the beam. Okay. So this is the force applied here. Okay. Now for this beam, if you cut a cross section, okay, if you cut a cross section anywhere, okay, for this particular one, you're going to end up with a rectangular cross section, right? Yeah, so that's for this one here. So if you're asked question is, can you calculate the stress at this x location? So the x location is the location from the force along the beam location. So at this location, right? So what would be the stress at this x location here, right? So what do? And you basically, you calculate sigma equal to mc over I, right? So you calculate this formula using mc over I. So c at here will be basically half of the thickness at here. So we're talking about the normal stress at the top or at the bottom edge, right? Okay. So and I at here, it's the second moment of area, because this is a rectangular cross section. So your I will be 1 over 12 W times T square. Okay, yeah, and M equal to F times X, of course, right? Yeah. So and C equal to T over 2. Okay, so if you substitute everything into it, okay, you're gonna get for this one here, sigma equal to 6 times F times X divided by W times T square. Okay, so for this particular cantilever beam, the stress at any location, X location here, okay, X location, we get our bending normal stress, which is this much. Okay, it's this much here. Okay. So now I can give you two different cases. Okay. So first case. Okay. Let's look at the first case here. So for the first case, and what I wanted to do is I want to maintain sigma constant. Okay, maintain the sigma constant. So think about it, right? So what does the sigma constant basically means? You cut a cross section at here. Here is the normal stress, bending normal stress, right? You cut a cross section somewhere here, you get another bending normal stress, okay? But I want to maintain a constant bending normal stress. It doesn't matter where you cut. Okay? It doesn't matter which cross section, or it doesn't matter which distance this x is. We want that sigma to be a constant. That's basically the idea of the so-called uniform strength cantilever beam. So at every location of x, you're going to try to maintain the same sigma here. Now, in order to do that, we can also keep this keep this t as constant. Okay, keep the t as constant. So coming back to this equation, look at that. If you want this one to be constant, and then also t is a constant, so that only leaves us with what now? This x over w now, right? So if you want sigma to be constant, and t is a constant already, so basically it's the same thickness, right? So you cut it anywhere, you got the same thickness t. Then that basically means your x over w equal to a constant. Okay? If you can keep your x over w ratio to be a constant, then this sigma will be a constant value. Okay? So let's call it small k parameter. So we get our x equal to k times w. And w is the parameter, is the width, right? This is the width of this cross section in here. Okay? The width of cross section. So technically speaking, x equal to kw, and I can draw basically, if I let x to be y-axis and w to be the x-axis, and this essentially tells us what? Essentially it's two straight lines, right? With a slope of a k. Okay, and k could be a negative, could be positive, right? Okay. So that got basically the relationship between x and w is this straight line. So you look at this drawing here. Here's your x, right? This is your x at here, and here's your w, right? If you relate to them, so this is the y-axis, this is your w-axis here. So now you can visualize if this is the side of the wall at here. Move this down a little bit. Okay, if this is the wall right here, and what would be the shape of this object now? T is a constant, so let's say this is a tape right here. Here's your F. Here's F here. So T is a constant. X and W maintain that relationship. So you basically get a triangle type of a shape, and then you will maintain a constant thickness, right? So that's basically the structure of this cantilever beam in order to realize the objective at here. That make sense? Yeah? That's called a constant stress. That's case number one, huh? And if you can maintain, so this is your x-axis direction. If you can maintain this relationship, okay, it doesn't matter where you cut. You cut it over here, you cut it over there, okay? And the stress on the top and the bottom, okay, anywhere along the beam will be a constant normal stress. Okay, that's case one. So let's look at the case number two. Okay, case number 2. And we starting point is still this stress, general normal stress. Okay, general normal stress. So in this second case here, we're gonna keep the sigma as constant, but this time we will keep the W as constant now. Okay, we'll keep the W as constant. Again, what is the W? W is the width, right? It's the width of the cross section. Okay, so if we keep the sigma constant, W in a constant, so that basically leaves us what? X over T squared equal to a constant. Okay, X equal to T squared constant, and equal to K. So meaning X equal to K times T squared. Okay, right? X equal to T squared. Now, in order to drawing it here, if this is X, if this is a T, then X equal to T squared give you a parabola, right? So here you got a parabola here. Okay. So that's basically the shape of this cantilever beam in order to keep sigma and W as constant. You get this type of a shape. So if you cut a cross section over here, anywhere, right, you get the same W. Okay, you get the same W, and the thickness T will be different, of course, depends on where you do the cutting. Okay. So these two cases, okay, will give you the so-called constant strength, or essentially it's a constant normal stress, basically. Okay. It's the second case that we actually will make use of for our gear tooth stress derivation, okay, stress analysis. Everything okay? So far so good? Okay. So now let's look at the next one for a gear now, okay, for a gear. This is a drawing of a gear tooth, so just one tooth at here, right? Just one tooth. Okay. Louis. Okay, so this equation is basically named after Louis. Okay. So I forgot which year now. 1892. Okay. So in 1892, so this Louis, okay, I'm not sure what's his last name. He actually discovered, okay, he discovered that within a gear tooth, okay, within a gear tooth, you can inscribe a constant strength parabola. You see the parabola here? You can inscribe a constant strength parabola here. So this one here is called constant strength parabola. Okay. So what is called constant strength parabola? That's basically the same type of structure as I showed you in the case number 2 at it here. If you visualize basically, if you visualize this gear tooth, if I draw it over here, probably, let's see, right? If I draw it over here, this is not the biggest one here, but basically you can draw a inscribed parabola, okay, inside this gear tooth, and then you can extend the line over there and then over here. So overall it's in a shape like this cantilever beam. Okay, so that's what Louis find out. You can inscribe a parabola here for any locations along this parabola. You got a constant, basically strength, constant normal stress, basically. Okay, and that parabola is tangent, okay, to the root location, okay, at this root location for the gear tooth. So that's this black line, the nature of this parabola here. Okay, yeah. So the following derivation, okay, essentially is all based on this constant strength parabola here to get this so-called Lewis equation. Okay, the Lewis equation. Before we derive the Lewis equation, another observation is basically if you cut a cross section, for example, anywhere along the gear tooth. So if I cut it over here, so if I cut it over here, it's like you cut it over here. Okay, sorry, like this. Is that good? Yeah. And if you cut it like this, then we can show that. Okay, we can show that. So here is the B location on the parabola, right? Here is the A location on the gear tooth profile. Okay, so we can easily show that the sigma A value is less than the sigma B value. So sigma A value is the value on the gear tooth involute surface, and B is on that constant parabola locus. Okay. So let's say, how do you show that? Essentially, if this is the distance from here to here, let's call that maybe distance. Let's call that distance C, for example. Okay, distance C. Okay, so you can see that for sigma A is equal to this WT. Let's consider this is the cantilever beam under the WT. So WT times C, and then at A location, okay. So at A location, you could be this. Let's say I call this AA. This is a BB. Okay. So AA has a width of T2, and BB has width of T1, for example. Okay. So that'll give us sigma A equal to W times the distance C is the moment, and then half of the thickness, so T2 over 2, and then divided by 1 over 12, the face width F times T2 cube. Okay, T2 cube. And that can be simplified into 6 times WTC over F. This is a FT2 squared. Okay, that's a sigma A. And then sigma B is equal to WT times C, T1 over 2, 1 over 12F, T1 cube, which is 6 times WT C over F T1 squared. Okay, that's the stress, normal stress at sigma A and sigma B value. So you can see T2 is what? Greater than T1, right? Then that means sigma A is less than sigma B. Okay? Yeah. So why I wanted to show you this is because the Lewis basically, instead of analyzing the gear tooth anywhere, so his equation will be focusing only on this constant strength parabola. So he formulates the gear tooth, the shape. It's not the original shape anymore. He formulated the gear tooth with the cantilever beam with the shape of this constant parabola, basically. Okay, yeah. So that's how he's basically doing this analysis for the gear tooth. Okay, yeah. So if you look at the root location, right? If you look at the root location, essentially it's like you have basically a cantilever beam. Okay, of course it's not a straight rectangular beam anymore. Okay, you have a WT applied here. So basically we're looking at the stress at the root location. Okay, that's where the critical location is. We can find the sigma equal to 6 times Wt times L over Ft squared. You see here, here is the length L, okay, from here to the end, the root, and T is the width of the root location. Wt is the transmitted load, so Wt times L is the torque, right? You know, just same derivation in here. So this is your sigma at the root location. Okay, yeah. Now you probably noticed that here Wr is neglected. Okay, it's neglected here. Okay, for Lewis equation derivation, it didn't consider Wr. Technically speaking, Wr should be considered, right? If you are really doing the actual analysis. So because why? If you look at this one here, what type of stress does Wr cause? Wr is pressing it. So it's going to cause what type of stress? The normal stress, right? And what type of stress does this Wt cause at the root location? It's a normal stress, but it's what? Tensile, right? So it's they are actually different direction, right? They're actually different direction. Okay? So technically you should, but the Lewis didn't consider that. Okay? This is actually one of the reasons for actual design, we actually need to take this into consideration. But for now, the Lewis equation didn't consider Wr. Now this is not the final form for the stress. So what happens is Lewis taking into some of the parameter here, and basically it's a sort of a geometrical form factor, form parameter. So formulating x parameter. So this is x, how it's defined. It's very simple. You know, basically you have your parabola tangent to the root location, then create a perpendicular line at here, and that line intersecting the center line at here, and then draw another horizontal. So this is your x distance. Okay, your x distance. And we can easily show that your x, okay, using similarity of triangles, similarity of basically triangles, you can show that x is related to the t and 4 and L like this. So we can rewrite this sigma, okay, into the following, into the following equation at here, into the following equation, and the p at here is the circular pitch. Okay, it's the circular pitch. So here's your p. Okay, here's your new. It's the same thing. Okay, just a different way of writing this stress at here. And now, what Lewis did is it defined a new parameter called the small y. Okay, define it as a 2/3 x times the small p, the circular pitch. Okay, it's the circular pitch. Okay. So this is basically the initial name for the so-called Lewis form factor. Okay, Lewis form factor. And then later, okay, it's transformed to slightly different. Instead of using circular pitch, and then we use actually diametral pitch. So we use a PD here. We call it diametral pitch. Okay, diametral pitch. Okay, just a second here. Let's see. Yeah, that's right. Sorry, go ahead. So let me write down here. So the capital Y is related to the small y, which is pi times small y. Yes?
On the sigma equation, you cancel the p?
This one here?
No, yeah.
We keep it. It's just like redundant, but yes, you technically you can cancel this, right? Okay. Yeah. But that's just the way the Lewis equation how it is formed. So it's using the so-called form factor. I'll explain what the form factor basically means here. Okay. Yeah. So this capital Y here, it's also basically called the Lewis form factor. Okay. Yeah. This is also form factor here. So let me move this down a little bit here. So this guy here, okay, it's the same name. So Lewis form factor. Okay. Yeah, Lewis form factor. So now with this notation, your sigma, okay, can be rewritten into a format like this now. Okay. So WT times diametral pitch over the phase width times the Lewis form factor. So this is where I need you to be a little bit vigilant. So the F here is not a force. The F here, the symbol is the phase width of the gear tooth. Okay? Yeah. So if you look at the notation here, this is the phase width for the gear tooth, okay? Not the force. All right? Yeah. Now this is basically what we call Lewis equation. Okay? One of the equations that we're going to use for gear analysis and design is an extended equation of this simple format. It's very much like this one, but it's adding a series number of factors to this equation here. But it's based on this one. Okay? Yeah. Any questions? Okay? Yeah. So the Y value, okay? The Y value here, there are two. In the textbook, there is a table 14-2. Relates the Y value with the number of teeth. Okay, so at the different number of teeth, you already got a Y value at here. Okay, and in my lecture notes, I have a curve table for the Y at a different pressure angle for different number of teeth. So as you can see, basically, as the number of teeth increasing, the Y value will be bigger. Okay, yeah. So let me ask a simple question here. Right, you see here. If number of teeth increase, Y will increase. So if you look at this Lewis equation, what's the effect on the stress now? The sigma will decrease or increase. You look at this equation here. If Y increase, the sigma will actually decrease, right? Yeah. That's something that you should need to bear in mind when you do the gear design. You will try out a different combination of number of teeth. Right? What are the effect of number of teeth on the calculated stress? This is one thing you need to be bearing in mind of here. Okay, choosing the number of teeth appropriately. Okay, so I'll explain this a little bit more here using that software for illustration in terms of what exactly is the form factor. Okay, yeah. So
sigma is still at the base, the root base.
Yes. Yeah, it's the same sigma. Yeah. Okay, so see you next week.